Welcome, everyone. On behalf of Forge College, I am absolutely thrilled to have you here for this explainer on testing, validation, and documentation for templates. Now, to give you a little map of where we are, this is part of the capstone, deploying a comprehensive Solana application module. That sits inside our Applying Solana Program Templates course, which is a key piece of the broader Programming with Solana track. In our previous lesson, we really rolled up our sleeves and heavily customized the Solana program template. We shifted files around, played with configuration, and wrote some actual logic. But today we're shifting gears from building to proving. We are going to strictly lock down the testing, validation, and documentation for that very template.
And that brings us to the ultimate million-dollar question. Does your custom template actually work? We all know that classic developer hubris, right? You just finished customizing the code. It compiled successfully on the first try. Or, okay, let's be real, maybe the fifth try. So obviously it's ready for mainnet, right? Wrong. Just because it compiles absolutely does not mean your on-chain data layouts are behaving the way you expect them to. We need concrete proof.
So here is our engineering blueprint for today. We're going to cover trust but verify, building the test harness, the 3 test vectors, investigating serialization mismatches, the debug report, and we'll wrap up with our conclusion and next steps. Let's jump right in.
Section 1. Trust but verify. It is time to start interrogating your code.
I really want us to approach testing not as some tedious, boring administrative chore you do at the end of a project, but as a rigorous, deliberate interrogation of your code. You need to put your program under the spotlight and ask it the tough questions. And the main suspect we are interrogating today is Borsh serialization. Now, Borsh is the process of converting your program's data types into a deterministic sequence of bytes for on-chain storage and retrieval. But here's the thing about Borsh. It has a very mischievous personality. It absolutely loves to hide extra padding zeros or quietly move your enum discriminants around when you aren't looking. If we want our Solana program to reliably store and retrieve state on-chain, we have to verify that Borsh is serializing our data exactly the way we think it is. All right, moving on to Section 2, building the test harness. Let's set up the lab work. We need to set up a validation harness right inside our existing customized template. Think of this as carefully setting up our scientific lab equipment before we start running any experiments. Our test harness is incredibly straightforward and relies on 3 concrete steps. First up, we write targeted Rust unit tests to actively exercise every single serialization path our program uses. Second, we build an optional, but highly recommended, CLI helper. This little tool is fantastic because it simply emits the hex-encoded payloads of our data, letting us inspect the bytes with our own 2 eyes. And third, we create a markdown file called debugreport.md. This is our logbook. It's where we record our expected results, our actual results, and any fixes we apply. But before we get too deep into the code weeds, let's establish exactly what we are testing. We use what's called a test vector. A test vector is simply a specific set of input values. We use these to represent both normal everyday operations and those weird, extreme edge cases. By locking in these exact inputs and checking the output, we confirm that our program, and specifically our account state structs and enum variants, behave with total determinism.
Which brings us to Section 3, the 3 test vectors. These are the specific suspects we must interrogate.
Our strategy for choosing inputs relies on a strict rule of 3. You can't just test one happy path and call it a day. No way. For every type you customize, you literally must create these 3 vectors. First is the canonical vector. This is your standard, typical data. It asserts normal, predictable serialization. Second is the minimal vector. Here, you want to exercise empty strings, zero-length vectors, or optional fields set to none. Does the program crash? Does it serialize to absolutely nothing? We need to know. And third is the boundary vector. This is where we aggressively push the limits with max-length strings and deeply nested enums. This trio ensures your blueprint holds up perfectly under pressure.
Okay, Section 4, investigating serialization mismatches. Time for a little crime scene investigation.
So, what actually happens when you run those meticulously crafted vectors and the tests fail? Boom, red text everywhere. Well, don't panic. Let's treat it exactly like a crime scene. It's time to put up the yellow tape and figure out what went wrong. I've got to tell you, there is honestly nothing quite as humbling in a developer's life as the expectation versus reality of running your first serialization test. You calculate that the bytes should be exactly 0, 1, 0, but the observed hex from your test run comes back as 0, 2. This mismatch usually means Borsh serialization sneaked in some implicit padding, or maybe a length prefix was added that you completely forgot about. It is a brutal reality check for sure, but it's exactly why we do this.
When you find a mismatch, you need to categorize exactly who the culprit is, using a clear mental model. If the very first bytes are different, your enum discriminant is likely in the wrong order. To fix it, serialize the variant tag all by itself to see what Borsh is actually doing. If you have a length mismatch, remember that Borsh often encodes string and vector lengths as little ending U32s. Serialize just the length to confirm that's what's happening. And if you see extra zeros, well, that is almost certainly implicit padding from fixed size types fighting for alignment. You can isolate that padding by serializing individual fields one by one.
Section 5, the debug report. Let's create that paper trail.
Once you have successfully interrogated your code, isolated those sneaky culprits, and solved the mismatches, well, science isn't really science unless you write it down. The crucial point here is this. Treat Borsh schemas as part of your program's public interface. It is not just internal plumbing that you can ignore. You must rigorously record your passing and failing vectors into your debug report.md. Note the expected hex, the observed hex, and the root cause fix. This ensures that any future changes to your layout remain completely traceable and, more importantly, mathematically auditable by anyone reviewing your code.
And finally, Section 6, Conclusion and Next Steps. Handing things off to assembly.
You've done the really hard work of validation. Now we prepare to hand it off for the next massive phase of our capstone project, which is assembly. Before you finish up today, you need to ensure these artifacts are locked in. Commit that full test suite with the expected hex vectors permanently hard-coded right in as literals. Save your debug report, document your versioning rules, and finally, the ultimate test. Run your tests in a totally fresh, clean repository clone to guarantee absolute reproducibility. In the next lesson, we're going to integrate these verified, rock-solid artifacts into the final capstone assembly process.
I'll leave you with this final thought today. Immutable proof. Verifiable code isn't just a nice-to-have. It is the absolute foundation of Web3. You can't just hope your blueprint matches reality. You have to prove it mathematically. Thank you so much for joining us for this explainer. Be sure to head over to forge.college to dive even deeper into this capstone project and explore all our other fascinating Web3 subjects. Keep learning, keep verifying, and I will see you in the next one.